So for this example, it's going to be our first time writing an approximating polynomial that's not centered at x equals 0. So far, the examples we've done, it's a little bit weird. It's like learning how to write the equation of a tangent line and then only ever finding the tangent to a function at the place where x equals 0. You could really find the tangent to a function at any place you wanted. So we could find an approximating polynomial that's focused at one particular place on that function. So we're going to write a series for e to the x at x equals 2. So I'm going to need to know f of 2, which is e squared. I'm going to need to know f prime of x so that I could figure out f prime of 2. F prime of x equals, oh, that's easy. So what's f double prime of x? Is also e to the x. So I'm getting a little break here because no matter what derivative I take of the function e to the x, the answer is going to be e to the x. So when I evaluate any derivative, so f prime of 2, f double prime of 2, f triple prime of 2, the fourth derivative of f at x equals 2, they're all going to be, so no matter which derivative I take of x is going to equal e to the x. So whatever derivative I evaluate at x equals 2 is going to be e squared. Now I just have to remember my little Taylor series pattern. So I'm going to make a whiteboard and write this out. All right, so at x equals 2, e to the x is going to equal, let's see, it's going to be f of 2, which is e squared, plus f prime of 2, which is e squared times x divided by 1 factorial, plus, oops, this one is not x. If our whole series is centered at x equals 2, then this is the factor, x minus 2. So this is going to be plus e squared over 2 factorial times x minus 2 squared, plus. And if I wanted to write a general term, that would be plus ... plus e to the n. Nope. E squared. E squared over n factorial times x minus 2 to the n. So that pattern that's in the notes, you have to memorize it. But you can see we've written a polynomial function that approximates the e to the x function and is not just centered at x equals 0. All right, so here's a released problem from an actual AP test. We've been given a statement that f of x is sine of x squared plus cosine of x, and we've been told that this here is the graph of the absolute value of the fifth derivative of f. Now that part is going to be helpful for part D when we talk about error, which is 9.3. So we're not going to need this graph for this part that we're going to do here. So part A, if you believed me and we memorized those Maclaurin series, then part A is going to be a piece of cake. It says write the first 4 non-zero terms of the Taylor series for sine of x about x equals 0, and write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. So, all right, so I wrote the first 4 terms. Really, you just want to have this memorized. If you don't have it memorized, you could stop and you can figure out the first several derivatives of the sine function, and you can evaluate all of them at x equals 0. And as long as you remember this pattern where you have x to the nth power divided by n factorial, you can put together this. So whether you put the plus sign here at the end or not, I was not a big deal. They want the first 4 terms. So that's sine of x squared. Sorry, that's sine of x, the first 4 non-zero terms. Could you figure out the first 4 non-zero terms of sine of x squared? Well, yeah. This doesn't even take any calculus, right? So sine of x squared is just going to be this same polynomial, but everywhere you see x, we're going to replace it with x squared. So it's going to be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial, which you could leave exactly like that, or you could simplify. So recall, it's not required that you simplify your results on the AP test, but there might be some other problem down the line where you're going to want to, or it would help you to have a simplified answer so that you could use it in your next step. But this answer gets full credit here. It's actually worth 3 points. 1 point for remembering the Maclaurin series for sine of x, and 2 more points for being able to replace all the x's with x squareds. All right, for part B, we've been asked to write the first 4 non-zero terms of the Taylor series for cosine. I bet that's worth a point, and all we have to do is remember this one. X to the 4th over 4 factorial minus x to the 6th over 6 factorial, and I needed 4 terms. I have 4 terms. And it says use that plus what you did in part A to write the first 4 terms of, the first 4 non-zero terms of f. So f of x is sine of x squared plus cosine of x. So I'm going to move that picture out of the back, and I'm going to put back our answer to part A, and I'm going to combine it with my answer so far in part B to get a final answer. All right, so I put back my answer for sine of x squared. These could have little plus dot dot dots, plus dot dot dot. So I need the first 4 terms of what I would get when I add this series to this series, because notice I'm adding sine of x squared to cosine of x. Okay, so that's going to equal, if I go and try to combine like terms in order, I'm going to get 1. I'm going to get, that's a negative 1/2 x squared and a positive 1x squared, so that's plus 1/2 x squared. I'm going to have, this is my only x to the 4th term, plus x to the 4th over 4 factorial. And then I'm going to have this, wow, this is going to be crazy. I have 2x to the 6th terms. That's going to be minus. So this whole crazy thing is going to get multiplied by x to the 6th. What do I have here? This is a negative 1 over 3 factorial. 3 factorial is 3 times 2 is 6, so 1/6. And it's like I factored my subtraction sign out here. And then, so this is going to be x to the 6th over 6 factorial. So 6 times 5 times 4 times 3 times... So 6 times 5 times 4 times 3 times 2 times 1 is 720. I could have just left this as 1 over 3 factorial plus 1 over 6 factorial. That's fine. You could simplify. Remember, you always have the right to not simplify. So you could leave this answer and notice 1, 2, 3, 4. There are 4 terms. Important to notice, just remember that when I got this 1/2 x squared term, that was from a positive 1x squared minus an x squared over 2. We have to do the combining to notice that that makes up, they're going to add together to give just 1 term, since those are like terms. So here is answer, full credit. And then this last problem that we're going to do, part C, we've been asked to find the 6th derivative of f at 0. And it's kind of like using the Taylor series formula backwards. Most of the time, I give you a function that I want a Taylor series for, and you have to take all the derivatives to make me the polynomial. This time, we have the polynomial, and we're going to use it backwards to figure out what the 6th derivative of f was at x equals 0. So remember the Taylor series the Taylor series sort of little formula, that polynomial is going to be f of 0 plus the first derivative add 0 over 1 factorial times x to the first plus the second derivative at 0 over 2 factorial times x squared plus dot dot dot. So the sixth derivative, well, the term that has x to the sixth in it is going to look like this. The term that has x to the sixth in it is going to be the sixth derivative of f at 0 over 6 factorial times x to the sixth. So I'm going to come here and look for the coefficient multiplying x to the sixth. If I can write it so I can get the 6 factorial back in the denominator, then whatever's left in the numerator, that's going to be the sixth derivative of f. So that was negative. I want a common denominator of 720. I'm going to multiply that 6 by 120. Sorry, that first fraction, 1/6 by 120 over 120. It's going to be 120 over 720. So it's going to make negative 121 over 6 factorial times x to the sixth. I'm looking for not the 6 factorial part, not the x to the sixth part, but this number here, this coefficient. That is the sixth derivative of f at x equals 0. So I would write f sixth derivative at 0 is equal to negative 121.